Right? So to sum up, we've got three laws. Boyle's, which is relating volume and pressure. Charles, which is relating pressure and volume and temperature, and Avogadro's, which is relating volume and number of moles of gas. These laws illustrate the volume of a gas and how it depends on pressure, temperature, and the number of moles of gas. If we take all three of these together, we can combine them, right, relating them to the volume, where it says our volume is going to be equal to some combined proportionality constant times the temperature and the number of moles of gas, and it's going to be inversely related to the pressure, where R is going to be this universal gas constant expressed in liters atmospheres per mole Kelvin, and we're going to rearrange it to get the very famous PV equals nRT. Well, I will give you this on a test. You probably want to memorize that. Right. Features of an ideal gas law. Right. This law is an equation for the state for a gas. If a particular gas's state can be described by its pressure, volume, temperature, and number of moles. So this number of moles here, right, we can rearrange, right, if we've got PV is equal to nRT, right, we can rearrange that and talk about N being PV over RT. So we've got something here in our gases that's going to be related to moles. And if we've got moles, do you think we're going to do stoichiometry? You betcha, we're going to do some stoichiometry with that. It is an empirical equation, and it is based on experimental measurements. Any gas that obeys this equation is said to behave ideally. And at the end, we'll see some non-ideal gases. Well, let's do an example. So a sample containing 3.35 moles of argon gas at a temperature of 13 degrees C and a pressure of 568 torr is heated at 56 degrees C and a pressure of 897 torr. Calculate the change in volume that occurs. Right? So what are we doing? Right? So we're trying to find our change in volume. We've been given our initial number of moles and our final number of moles as being the same. We didn't change any moles to it. Our initial pressure, we're going to convert that from torr into atmospheres. Right? The reason why we're doing that is because our R value, our R constant, is going to be in liters times atmospheres per mole times Kelvin. Right? Liters, atmospheres, mole, Kelvin. So we've got to have this in atmospheres. And we've got to have this temperature over here, T1, in Kelvin. We've been given pressure 1. We've got a change in pressure. Here we've got a change in temperature from 286 to 329 Kelvin. Right, so we're changing two variables at one time. And ordinarily, if you were changing two variables at one time, you're going to have a bad day. But the nice thing about the ideal gas law is that we can change lots of variables at the same time and still work with it. Right, so we're going to apply our ideal gas law. Our pressure times volume is equal to the number of moles of gas times the temperature, where R is 0.08206 liters times atmospheres per moles times Kelvin. So we're going to rearrange to solve for volume 1. We do PV equals nRT. We know N1. We always know R. We know T1 and we know P. So it's 0.35 moles times R, 0.0821, times, and then we got liters atmosphere moles Kelvin times 286 Kelvin, right? All of our units will cancel out, and we're left with 11 liters. We do the same thing for V2. Right? We can calculate V2 by doing N2 times R times T2 over P, and we get 0.35 moles times 0.821 liters times atmospheres per mole Kelvin. Our moles cancel out, our atmospheres cancel out, our Kelvins cancel out, because we're multiplying by 329 Kelvin, and we end up with 8 liters. So we need to figure out the change in volume. All we do is do V2 minus V1, final minus initial. 8 liters minus 11 liters is minus 3. Our change is minus 3 liters. Now, note that this is a change, right? You can have a change in volume of minus 3 liters. You can have a change in moles of minus 3 moles. You can have a change in temperature of minus 10 Kelvin. What you cannot have, right? Notice that word in there that I've been saying each time is change in. So delta V, delta T, delta N number of moles. You can have a negative number with that, but you cannot have a negative number of moles, right? Your number of moles has to be positive. So when you're doing PV equals nRT, your pressure has to be positive. Your number of moles has to be positive. Your volume has to be positive. Your temperature in Kelvin has to be positive. And all those values have to be positive. The change in them, that can be negative, but the numbers themselves are always going to be positive. The change in volume is negative because the volume decreases. We begin our discussion about gas phase stoichiometry. We're looking at the volume of an ideal gas. So the volume of a gas, as derived from the ideal gas law, is going to be, for 1 mole of gas, we're going to solve V, so the volume will be equal to N, the number of moles of gas, times R, the ideal gas constant, times the temperature in Kelvin, divided by the pressure. So 1 mole of gas at 273 Kelvin is going to be 22.4 liters. So 22.42 liters is the molar volume of an ideal gas. And knowing this is useful because it gives us a place to kind of provide a reference for other things. So if you say, what is the volume of 1 mole of gas at 2 atmospheres of pressure? Well, it's going to go down by half, right? It's going to be 11. What is the number of moles in 44 liters of gas at standard temperature and pressure? Well, then that's going to be 2 moles, right? So you can look at this as a useful reference point. And so how big is 22 liters, 22.4 liters? If you were like me and you're like and you're a typical American, you are not used to measuring things in liters. So you may not have an immediate sense of what a liter is the same way you would have a sense of what a gallon is. But I would wager that probably everybody has seen a 2-liter soda bottle at some point. So you're looking at 11 2-liter soda bottles. And that's 1 mole of gas is going to become 11 2-liter soda bottles. So this is at what we call standard temperature and pressure. And just like we had a naught value, a standard state condition, we're going to have, in thermochemistry, we're going to have a standard temperature and pressure when we're dealing with gases. So STP, right, is going to be a common reference for gases, and that's going to be represented with 1 atmosphere of pressure and at 0 degrees Celsius, so 273.2 Kelvin. And that's our standard temperature and pressure, just like the name for the racing car parts, right? So let's look at an example. A sample of methane gas has a volume of 2.8 liters at 25 degrees C, and 1.65 atmospheres was mixed with a sample of oxygen having a volume of 35 liters at 31 degrees C and 1.2 atmospheres. The mixture was ignited to form carbon dioxide and water. Calculate the volume of carbon dioxide formed when the pressure, at a pressure of 2 atmospheres and a temperature of 125 degrees Celsius, right? So the first thing you're going to want to do, like any of these other stoichiometry problems, is moles, right? Because if PV equals nRT, right, we can find moles by doing pressure times the volume over RT. So we're going to try to find moles, and then once we got everything into moles, then we can do our stoichiometry, and we can go look at our mole-to-mole relationship from a balanced chemical equation, and then put it back into whatever units they're looking for. And so the information that we have available, we've got, so they're making a nice little table here, right? And I kind of like how they're doing this. They got this CH4, the O2, and the CO2. We know the pressure of each of these that was given. We know the volume of each of these that was given. Right? We're trying to solve ultimately for this volume. And we know the temperature of each of these that was given. right? What we'll want to do next is figure out the number of moles of each of these things. So we're going to use this information here, the pressure, volume, and temperature, to figure out moles of methane, the pressure, volume, and temperature to figure out moles of oxygen. We'll do our balanced chemical equation with our moles and our moles, figure out which one is the limiting reactant, if any, and then figure out how many moles of CO2, convert that up into a volume. So we'll do PV equals nRT twice, once to find moles for each of the reactants, and then again, once we found the moles of product, to find the volume of product. So we're going to have our balanced chemical description of the reaction. We've got an unbalanced chemical equation. So step 0 is we've got to balance that chemical equation. All right, got to get it into a BCE. We're going to balance that out, and we'll get CH4 gas plus O2 gas, 2 O2 gas because it's CO2 and 2 H2Os. Then we've got to figure out the limiting reactant. So our number of moles of methane is going to be PV over RT. We'll then plug in the appropriate values. So 1.65 atmospheres, that was from our table, 2.0 liters. We're going to divide by 0.0821 liters atmospheres moles Kelvin, that's R, and we'll divide by the temperature in Kelvin. And we end up with 0.189 moles of methane. We find the number of moles of oxygen in the same way. We take the pressure and volume of the oxygen divided by R and the temperature of the oxygen. So 1.25 atmospheres times 35 liters divided by 0.821 liters atmospheres mole Kelvin divided by 304 Kelvin, and we get 1.75 moles, right? The stoichiometry is not a simple one-to-one, so we got to figure out which one is going to give us the least amount of product and therefore is the limiting reactant. In the balanced chemical equation, 1 mole of CH4 requires 2 moles of oxygen. Thus, the 2 moles of oxygen required by the 0.189 moles of CH4 can be calculated as follows. So 0.189 moles of methane times 2 moles of oxygen per mole of methane, giving us 0.378 moles of oxygen, which means that we're going to need, in this case, if we take 32 and we divide it by 2, we're going to end up with 16. So that's going to be oxygen, diatomic oxygen.